So today we shall try to look at some of the constrained optimization problems that we have avoided so far. So far the only thing that we have constrained our search space to is the fact that these perturbations, the functions g that we have chosen, they had better vanish at the endpoints, and that too we relaxed on occasions when we said that okay, one of the endpoints lies on a manifold, right, and we have derived something known as the transversality conditions. So today we shall start to look at these problems where apart from trying to minimize some cost functional, you have to also meet certain constraints. And I will put it to you that we have actually seen such examples during our discussions previously when we spoke about things such as the Dido's problem, yeah, because the length was constrained and you had to enclose the maximum area subject to this length constraint. Similarly, the catenary equation, which is where you hang a chain or a cable across two towers, right. So the length of this cable was a given constraint, and according to the length you then try to find out what the equation of that curve would be like. So these are definitely strong enough motivations for us to look into the constrained scenario, right. Okay. So let us pose the problem in this manner. So this is the cost function that we have to minimize, okay. Of course, we will say that these are given and okay, this is the constraint that we have to also satisfy. It could be given by something such as this. It is an integral constraint, okay. So let us make that clear. An integral constraint like so, minus let us say C0. So it is an equality constraint, fits in with what we discussed in case of finite dimensions, right. Remember we had those H, the equality constraints defined by H1, H2, so on and so forth, and then we took the grad and found that, argued at least, we did not completely exhaustively prove it, but we argued at least that, well, this grad of f must be spanned by the grad of h's when the grad of h's were linearly independent, which is to say that the point x star was a regular point. Quite a lot of ideas, right, which we have to now seemingly translate from the finite dimension to this infinite dimensional problem. For the time being we are just considering one constraint, and for the most part you will see that this kind of covers a wide array of problems in calculus of variations, even with just one integral constraint like so. Now, what would that condition on regularity turn out to be like in this case? So what was at the heart of this regularity? If you just try to draw a mental picture, I am talking about the finite dimensional case. Suppose you had two constraints, one being a parabola and the second being a circle. Okay, it is a badly drawn circle, but never mind. Now, if you look at all those points which satisfy both of these constraints, it would turn out to be a singleton point here, that is this origin. But the problem was, when you took the gradient of these fellows at the origin, that is when you looked at this constraint in the differential form, what would it turn out to be like? Well, the gradient would point in this direction, and therefore you would perceive that your tangent space would be along this direction, right? So mistakenly what you would do, because if you miss the fact that this is not a regular point, you would tend to think that you can pick candidate points like so in a neighborhood of the origin, and those are still legitimate points that satisfy the constraints, whereas they actually aren't. That's what lack of regularity does, right? So essentially lack of regularity shows up more points or more candidates than are actually present. So when does the case become degenerate? In situations such as this. Of course in 2D, if you have two curves that are kind of tangential to each other, then there's only one point at which they intersect. Even if they're not tangential, well, a circle and a parabola would probably at most intersect at only 2 points. But if they do intersect at 2 points, you see their gradients will not be identical at those 2 points, and even by looking at the gradients you will be able to infer that it's only a singleton point. So therein lies the catch. Yes. Now we turn our attention to this infinite dimensional problem where we cannot draw these beautiful pictures like we draw in Euclidean spaces, and yet we shall see that at least at an intuitive level it's the same idea that forces us to look at this idea of regularity. So what is a regular point here? A point here would be a function, because there is a space of functions, so every point on this function space is a function, not a point on Euclidean space like it looks. Okay, consider this situation where you have two transmission towers, okay, and I give you a length of cable which is exactly equal to the distance separating these two, right? So that the only way to string the cable across these two is through this straight line here, yeah. In other words, there's exactly one candidate that meets the constraint, and in a neighborhood of this candidate there is no other candidate which satisfies this constraint, right? Which means essentially that the actual original cost function becomes immaterial. Doesn't matter what cost function I have asked you to minimize or maximize or do whatever, the only function that satisfies the criteria is this fellow. So perforce this becomes your only candidate, and therefore the cost function ceases to be of any significance. Now this is exactly the kind of degenerate case that we wish to avoid. What is it that characterizes this degenerate case mathematically speaking? Yeah, okay, this is a very specific example where a length of the cable is exactly the constraint, and that's exactly equal to the distance separating these two transmission towers. But essentially, would you agree if I said that, well, this candidate actually extremizes the constraint alone? If you look at this JC here, this fellow actually extremizes the constraint alone. So we have to be very wary of the candidates that we pick or search for, and we have to ensure that the candidate should not extremize the constraint equation alone. If it does, then there's nothing else in the neighborhood of the constraint or of the constraint set. While staying within the constraint set, you cannot find any other legitimate candidate. And then there's of course no point in searching for something that extremizes this, because that's the only candidate that's remaining there. So that would be the degenerate situation in our function space. We have to be very wary. Remember in the finite dimensional case we said that okay, you had this grad h dot product with the different directions that you assigned, yeah, and then you said that along these directions where the grad h dot di, grad hi dot di, and so on and so forth, and then finally we argued that okay, these are our tangent directions. So this grad f must be spanned by the grad h's, so that along the legitimate directions of motion the grad f is 0, yeah, because it does not change, because if it does change along one direction, then along the opposite direction it will probably do better in terms of minimizing the function, right. So that was the argument we presented. What we shall try to do today is to present a more rigorous proof, but that will involve a certain result that we shall not prove. That particular result is the inverse function theorem. Most of you would probably be aware of the fact that when a function is a bijection, bijection means it's one to one as well as onto, yeah, then it's invertible, right? Alright. Now, this function, this theorem is actually quite powerful in the sense that it says that if you have a function which is got a, say, a continuous derivative at a certain point and the derivative does not happen to be 0, okay, then at least locally in a small neighborhood around that, okay, so suppose you have the domain of a function here and this is the codomain. So suppose you have this point which maps under the function to this point here, and suppose it is differentiable here and it does not, the derivative does not vanish here. Then you can always find a small enough neighborhood here from which you can actually cook up an inverse map. Okay, we are not going to prove this, but we are going to just take this as a fact because this will take us too far afield from the objectives of this course. But that is what this does, okay. So suppose you have a function. Now if you extend this to functions of multiple variables, of course that non-zero derivative will change to a non-singular Jacobian, because of course if you have a function in multiple variables, then the derivative of that would be replaced by the Jacobian. Non-zero derivative, non-singular Jacobian, right? Okay. So this is essentially the idea of the inverse function theorem, and that is all we are going to essentially use for our purposes, because we are not giving an explicit proof of this fact why this is going to be true. This actually is true even for functions of complex variables, okay. So it is a general result from analysis, functional analysis. Alright, now let us consider the following setup. Let us have this function phi, okay, which does what exactly? Here is what the function phi does. So you have, remember this is j and this is jc, right. So we take this, remember the perturbations that we took were the g's, right, the vanishing perturbations, g which had ga is equal to gb is equal to 0, right. So the candidates we were searching for was, suppose you find a y, then you take y plus alpha g in such a manner that ga and gb are both equal to 0. In between they can do anything, but at the terminal points they must vanish. So now we are going to take this in such a way that this one picks out a pair of real numbers. You can think of them as something that is residing inside R2. And what do? Well, they do the following. Right. So it essentially takes in two of these real numbers. These g's are exactly some well chosen, some suitably chosen vanishing perturbations according to our requirements. They have to vanish at the endpoints, that is the only requirement. Now, very crucially, what can we say about this? See, if you have to satisfy the constraint, then even after the perturbation, this should also vanish. Yeah. So let's, and please interrupt me, feel free to interrupt me you have any doubts at this point, it's important to understand this. What we are saying is, this is a function which takes these two numbers, so its domain can be thought of as something like this, which is this direction is alpha 1 and this direction is alpha 2, like so. So this is its domain, and its codomain would be something that looks like this. Do you agree? Only for the, except for the fact that now if you have to meet the constraint, you are essentially confined to only points on the x-axis. Yeah? Is this clear? Because obviously if you don't sit on this x-axis, then you will have JC assuming some non-zero values, which means that you are not meeting the constraint condition anyway. And that's anyway something we don't care about, because we need to only search over those candidates where the constraints are satisfied. Correct? So this is the domain, this is the codomain. You pick an alpha 1 and alpha 2 subject to some G1 and G2 that have been already picked up. I am going to find a point here on this x-axis, which is the J axis here. Yeah? Alright. So this mapping is done by this phi. Okay. So suppose I have a certain point here which claims to be doing the best in terms of minimizing J while meeting the constraint JC. What does it mean? It means that while satisfying JC is equal to 0, I cannot move to the left of this point. If I did, then I would have actually done better at minimizing J while satisfying this condition simultaneously. Which means that if there is a small little neighborhood around this point where an inverse map exists, my case is doomed. Think of the reverse argument I am making here, because I am eventually going to use that inverse function theorem that I just mentioned a while back. What am I saying here? I am saying that if whatever you do here with this phi, which is a mapping from this variables alpha 1 and alpha 2 to these objects here, right? So this essentially will translate to something like this, some non-zero term here and some zero term here, right? That corresponds to a point on the x-axis. Now if this Jacobian of phi with respect to alpha 1 and alpha 2 is non-singular, I am taking one more step back. If the Jacobian of phi with respect to alpha 1 and alpha 2 is non-singular at a certain point, like at a certain point that alpha 1 and alpha 2 that I have picked up here, which has landed me up here, then in a small neighborhood around this, I will be able to do a bijection and map it back here. What does that mean? That means there is a choice of some alpha 1, alpha 2 which will allow me to do better than this point. But by my claim, this is the best. So if without loss of generality, because I am assured now that there is a neighborhood, of course that neighborhood, any neighborhood of this will include a small stretch, no matter howsoever small a stretch on the left along this axis. Yeah, any open ball that you draw around this point here will include points to the left of this. Therefore, at points to the left of this, you will be able to map, at least locally, invert the function and map to some point. Maybe this was your original alpha 1, alpha 2. You will be able to draw some point here and maybe in some neighborhood here, some alpha 1 prime and alpha 2 prime, which will land you up in a point such as this. That means a small enough perturbation from the so-called optima allows me to do better than the optima, which means that this fellow wasn't an optima or an extrema to begin with. You see? So the only way to circumvent this issue is, where was the problem? The problem was the existence of a non-singular Jacobian. Because the moment you have a non-singular Jacobian, inverse function theorem tells you that you will always be able to do this inverse mapping because of the bijection. And so you will have points to the left of this which have a pre-image here, which means that there are candidate legitimate perturbations from your so-called optima which does actually better than the optima. And that's completely ridiculous, isn't it? In order to rule that out, the only possibility is that the Jacobian of this phi with respect to this alpha 1 and alpha 2 must be singular. The Jacobian of this with respect to this alpha 1 and alpha 2 will be a 2 by 2 matrix. So what will that Jacobian be? This fellow's partial with respect to alpha 1, that's the 1 1 entry. This fellow's partial with respect to alpha 2, that's the 1 2 entry. This fellow's partial with respect to alpha 1, that's the 2 1 entry. And this fellow's partial with respect to alpha 2, that's the 2 2 entry. Yes? So if you pull out the G1 and G2 as a vector on the right, what happens? What are you essentially asking for here? Because G1 and G2 were in your hands, vanishing perturbations. They need not be 0. So essentially what you are saying is that this fellow here, pay very careful attention, at some y star along the direction of G1 and this fellow here at some y star along the direction G2 and JC at y star along the direction G1, JC at some y star along the direction G2 must be singular, isn't it? You've already seen the partial derivatives, right? Those are the first variations that pop up immediately. So you know already, except for the fact that instead of 1 alpha now we have alpha 1 and alpha 2. That changes nothing. You are essentially taking a partial with respect to one of those variables at a time, either with respect to alpha 1 or with respect to alpha 2. So it would be this. So this fellow has to be singular. What does it mean? That one row is a scaled version of the other. Of course, you might say, oh, hang on, what if this is 0? One of them is 0. Well, if this is 0 for all possible G1 that you choose, then you are already in a degenerate situation, isn't it? And that's exactly what we discussed, right? We are already considering that we are not in the degenerate case. So there are a number of a plethora of legitimate candidates which satisfy the constraint, so that there is not a single candidate which satisfies, and in its neighborhood there is no other candidate which satisfies the constraint. There are already a bunch of candidates which satisfy the constraint. That's at least that's how your point is, that's how your candidate is chosen, right? Not a degenerate situation, in which case you can always choose something that makes this non-zero. I mean, at least this one non-zero. Now what does it then mean? It simply means that first you look at this, the ratio between these two, and find out lambda 0 y star here with respect to G1 plus, okay, maybe you call it lambda 0 star because of the optimality condition invoked here, and you see so what do? You solve this equation assuming that this fellow is not equal to, this lambda 0 is not equal to 0, because if lambda 0 is equal to 0, this later on we shall call as the abnormal multiplier. In the finite dimensional case, you probably didn't see this appear because you simply went ahead and divided this because you assumed it was a regular point. But now if you write it in this manner, either this fellow is 0 or it is non-zero. If this is 0, then what it essentially means is that you cannot find a single G1 such that this is non-zero, which means that any perturbation, and it's done. So it basically extremizes the constraint itself, which is the degenerate situation. And if lambda 0 is not equal to 0, just go ahead and divide by lambda 0 here and call it lambda 1 hat, and you're back to the usual stuff, right? So this is how you, in the first case, you solve for this, for some g1 such that, you know, this lambda 0 star does not by default become equal to 0. And you will be able to do that in case it is not a degenerate situation. Okay? Because if this fellow is already 0 for all possible g1s, then lambda 0 star has to be 0. That's the situation when lambda 0 star is equal to 0. Unless this fellow is going to be 0 for every g1, you find that g1 for which this is not 0, and then lambda 0 star will also not be 0. That's the other way of saying things. Is that clear? So that means, go ahead and solve for this lambda 0 star and lambda 1 star. Of course, there are several values, it's just a ratio, right? Ultimately, that lambda 1 star by lambda 0 star is the ratio that you are finding out. But with that same ratio chosen, because they are going to be linearly dependent, it will also satisfy. So, solve for lambda 0 star, lambda 1 star, and that same, the same pair of lambda 0 star and lambda 1 star satisfies what? Satisfies what? I'll just replace the g1 by g2 here. Yes? So, lambda 0 star, first variation of this with respect to g2 plus lambda 1 star, first variation of jc at y star along the direction of g2 is equal to 0. And I am saying my proof is done because the choice of g2 is arbitrary. That's the reason I started with one function more than necessary, right? Earlier I used to just consider one variable alpha, now I considered alpha 1 and alpha 2, because that allows me to play around with this g1 in such a way to make sure that this is not 0, provided it's not a degenerate situation. If it's a degenerate situation, then it is 0. And there's no point in seeking for an extrema. Whatever satisfies your constraint by default becomes your extrema for all possible cost functions. After all, there is only one legitimate candidate sitting in your constraint set. So whatever filter you want to pass it through, whatever cost function you want to pass it through, that's the only fellow that passes through it. There's no point in even asking the question as to who is the optima or extrema. It's only one person. Yeah. On the other hand, if that is not the situation, you will always be able to find a g1 such that this fellow is not 0. There is some direction along which this doesn't vanish. Choose that as your g1, solve for lambda 0 star and lambda 1 star, invoke that lambda 0 star and lambda 1 star on this second condition, the row dependency of the Jacobian. Yeah, and now you arrive at this condition, but there was no restriction imposed on G2 to begin with except for the fact that G2 is a vanishing perturbation. So now if this is true for all possible G2, this actually gives you this formulation due to Lagrange, isn't it? Now you can replace this G2 with any G which satisfies the condition that GA is equal to GB is equal to 0. And what it essentially says is exactly what we had hinted at when we discussed finite dimensional optimization, that the grad of F is a linear combination of the grad of H's, and the linear combinations, the scalars, the scaling factors were given by the Lagrange multipliers. Here also there is a single Lagrange multiplier here because there is a single constraint here. If you go back now, there is a deep connection now, and that is again not surprising. We had dot products, if you remember, when we talked about dot products or inner products, when we talked about Euclidean spaces and finite dimensional optimization problems, right? And you might suddenly wonder what happened to that. What are inner products in function spaces? Anyone's aware? You've actually done that. You're all familiar with Fourier series for periodic functions. You remember you had cos nx sine mx dx, yeah, over a complete period. What did this turn out to be? If n is not equal to m, 0, right? Yeah, and if you had sine nx or sine squared nx, what did that turn out to be? Of course, you had to adjust with that 1 by 2 pi the periodicity, and you could always get some non-zero number. So this is essentially the idea of orthogonality, because this is the idea of inner product over function spaces, okay. So when you take two functions and you take their product, of course in case of complex functions you have to take their complex conjugates, that's a given because of the field over which you are taking this. So inner products only exist over vector spaces that are defined over either the complex field or the real field. In the real field they are bilinear, okay. Whether it's the first argument or the second argument, the inner product is going to be linear in both. In the complex field there's something funny that happens, it's just sesquilinear. It's not bilinear anymore because of the conjugation that happens, right. So those are some of the properties of inner product spaces. If you've done a course on linear algebra at some point, you might have already encountered them. Now the idea of inner product extends here as well. This is also a vector space, the function space is also a vector space over the real field, and this is how we define the inner product. There are properties of the inner product, and if you look at those properties you will immediately see that this candidate f1, f2, if you take f1 and f2 dx, that is actually an inner product, okay. And you can carry out processes such as if you've heard of this Gram-Schmidt orthogonalization, you can do exactly similar things on these spaces as well. The only difference being that now of course these need not be finite dimensional unless I restrict them to be. So for example, I say I look at only the vector space of polynomials having degree no more than 3 or 4. In that case it's a restriction, but in general polynomials will span an infinite dimensional vector space, right. So what I'm trying to say is that once you keep this in mind at the back of your mind as an inner product, you'll see that all of this makes sense, and as does the idea of tangent spaces. It's basically along those directions. Directions are now defined by the functions g, not by some physical direction like you can do in a Euclidean space, okay. So what I'm putting to you here is that you can use exactly similar argument and it will be even more tangible and easier to prove if you go back now to your finite dimensional optimization problem, yeah, and look at this and try to justify this more rigorously like we have done here. The only thing we haven't proved here in this step, of course I shouldn't say only to trivialize it, is the inverse function theorem, but again as I said that's not within the purview of this course. If you are interested, I would encourage you strongly to go through any book on functional analysis and you will find a rigorous treatment of the same, right. So this is essentially a justification. Go back and try to fill the gaps that we had left behind. What was the main gap? The main gap was that we had gone only one side. We had said if this condition is satisfied, this is a tangent space. The other side was we just kind of did a slight hand waving justification and said if this is a tangent space then this must satisfy this, right. So both of those sides we did not rigorously justify. That was the gap. Otherwise we kind of argued in a very intuitive manner as to why this Lagrange multiplier condition must hold, particularly when that point is a regular point, right. But now you have a more rigorous treatment of the same. This is exactly, you can replicate these steps in your finite dimensional case. So take that as an exercise to try and do that and convince yourself, okay. So this is an important result, the fact that you can go from a constrained optimization problem to an unconstrained optimization problem, provided you now make this mental change that I will look at L plus lambda m as my modified Lagrangian and seek not just the optimal y but also the optimal lambda. These lambdas are still numbers, by the way, yeah. So that's the good thing. These are still some constant numbers because of the fact that this is an integral constraint. We will discuss more about this in the ensuing lectures. But now, if you just treat it in this manner, by exactly similar reasoning as we employed for the finite dimensional optimization problem, we can now invoke the Euler-Lagrange condition on this L hat instead of the L, okay. and that is exactly what we shall see. We shall do a bit of warm up. You can also think of this as some sort of a tutorial of sorts. We shall actually try to explicitly characterize the catenary and the solution to Diderot's problem in view of this new framework that we have just justified.